Hello everyone, my name is Wanu Chu and I'm from the Autonomous Robots and Control Lab at the University of Oklahoma. In this video, I'll be presenting data-based MHE for Agile quadrotor flight. Quadrotors are useful for many applications such as mining, explorations, inspections, and search and rescue missions. One of the general aims of the robotics community today is working towards improving the drone's utility by maximizing the distance it can cover in a single flight. There's been significant advancements in the performance of the quadrotors controllers utilizing data-driven techniques, reaching speeds of up to 70 kilometers per hour. However, generally these performances were achieved in motion capture labs where the full system states were given. The onboard state estimation capabilities has a fair ways to catch up to the capabilities of the controllers for real-time deployment, as the basis of the performance of these controllers are that it has accurate knowledge of the system states. Difficulty with acquiring accurate knowledge of the system arises with the high level of aerodynamic disturbances that the quadrotors experience performing agile flights. The dynamic model of the quadrotor that is widely used only considers the propeller lift. However, the aerodynamic forces that the quadrotors experience are a combination of lift, rotor drag, interaction between the propellers, and the drag from the fuselage. The given model can be okay at lower velocities, but when flying at the speeds that we're trying to achieve, these turbulent disturbances will render this model inaccurate. Utilizing a kinematic model can help with this issue, given that the sensors can accurately capture the entire dynamics of the system. However, the kinematic model will struggle with tolerating noise and uncertainties, and it will not be able to perform parameter estimations such as estimating an unknown payload mass. If we can use accurate dynamic model of the system, this will be superior to using a kinematic model for state estimation, as it can provide higher level of detail of system dynamics to our state estimator. As mentioned previously, data-driven techniques have become popular for improving the performance of the controllers. Of these methods, we proposed extending the utilization of Gaussian process models to learn the unmodelled disturbances to provide model corrections. Gaussian process augmented dynamic models have been proven to be effective in improving the performance of a model predictive controller. Here, we take advantage of the duality of the model predictive control and moving horizon estimation methods to extend the data-driven techniques shown in the literature to enhance the accuracy of the MHE. We first collect flight data, and using the following equations, we compute the model errors. All the required measurements for this is only collected using onboard measurements, which significantly reduces the complexity of the data collection step by removing the need for ground truth data, which is a common requirement for these methods that involve machine learning techniques. We compute the error between the measurement and the model propagation with the known inputs to the system, and we map this against acceleration measurements using Gaussian processes. This allows us to estimate the expected model errors from the current and new measurements to improve the accuracy of the model. Furthermore, since the data points in the estimation horizon are repeated, only a single point computation from the GP models are required at every time step, which minimizes the computational burden of the GP. We conducted simulation and experimental studies comparing the performance of our MHE against MHEs with a kinematic model and a dynamic model. From our simulation studies, we found that at lower noise levels, kinematic-based MHE performed better. However, with the increased noise levels, GP MHE displays slightly improved robustness. The GP models improved the accuracy of the dynamic model-based MHE by 30% for orientation states and 15% for velocity states at the highest noise levels. Furthermore, it demonstrated the capabilities of estimating varying payload mass accurately with the improved state estimation performances of up to 40% for orientation states and 19% for velocity states. Lastly, the experimental studies using the Neurobeam dataset from the University of Zurich Robotics and Perception Group further validated our findings in improving the accuracy of dynamic model-based MHE by 26% for orientation states and 14.5% for velocity states. For more details on this data-based moving horizon estimation methods, please check out our paper, Data-Based MHE for Agile Quadrotor Flight.